And now for something completely different.
Or not.
So I've known Don for far too long.
Too long.
Don is an academic who's now at Warwick University, does an awful lot of work, very inspiring and novel work on exoplanet detection, and he's going to talk to us about ET Phone Home. Don?
Thank you, Stuart. I've got to say, this is the Faraday Theatre. I mean, this is on Christmas every year, and I'm here, and you're watching. But despite that, it's great, isn't it? What a theatre. Anyway, so I'm going to talk about exoplanets and aliens today. And I am an academic, right? So I'm not going to give you science fiction. Well, not really. I just hope that you can all take something away from this lecture. So here's an overview of what we're going to talk about. And I've been fortunate to come on at this point in the day. There'll be a little bit of repetition, which I'll go through very quickly, just to give you, we need to talk about scales and things to understand how likely it is that we will be able to meet our aliens. But of course, I am a scientist, and we're going to talk about facts as well. And we're going to talk about exoplanets as well, and then we're going to try and see our aliens in terms of these exoplanets. And we'll talk about the prospects of finding life, not in our solar system, but externally. And then I'll leave you with that final question: is there really likely to be aliens? So let's get a move on then. So we've already had some of this. Chris and Abby both went through some of these in a more diagrammatic format than this. But just look at these numbers. I mean, okay, Hyde Park, etc. But look how big that is. 28 million miles is the distance to the nearest star apart from the sun. That is a huge amount of time. And a chemical rocket, our fastest chemical rocket, will take the best part of 100,000 years. So, and that's the nearest star apart from the sun. So moving around the galaxy is not something that we can easily do, or we can do with our technology. It's just going to have to be something a bit more advanced than that. I'll just put this up. Then the other thing you need to think about is our place in the universe, how long we have existed. And here's a few things that you might like to look at to give you some idea of the ages in the universe. The universe is 14 billion years old. The Earth, okay, 4.57, whatever it is, billion years old. So you can see the Earth has only existed for a third of the duration of the universe itself. First human beings, which are not like us, appeared 2 million years ago, but we've been technically capable for maybe 150 years. 150 years out of 14 billion years. So you just need to think this. Some very simple things that you can think about now. What is the likelihood of meeting a civilization like us? 150 years out of 14 billion years. It's diminishingly small. In fact, the most likely kind of civilization that we would find or exists is a civilization that is millions of years more advanced than us, maybe billions of years. So why would they be interested in us? We would be the equivalent of amoeba on the beach to them. So why would they be interested? Well, they might be interested because they're seeing how early civilizations develop, how long they last, that sort of thing. But the likelihood is we would not recognize them. Can you imagine what our civilization, human beings, would look like with several hundred million years of evolution? It's going to look very different to this, for sure. So just think about that. Anyway, so let's get a bit more sciencey now. Those are some thoughts for you to take away and think about. But we can actually try and put numbers to this now. So there's an equation coming here, but don't worry that it's an equation. All you've got to think about are the things that are most likely to be needed to understand if there's civilizations in the galaxy. So surely the numbers of stars must be important. So you can see, in fact, all of these terms here, all of these parameters are things that are used to define whether or not, or to work out, there are likely to be civilizations. So let's go through them very quickly. The number of stars in our galaxy is given that symbol. The fraction of stars that have planets around them. Okay, that sounds reasonable. Obviously, if you don't have many planets around stars, then you're not likely to have many civilizations. The number of planets per star that can sustain life. Well, that's probably starting to get a bit risky, that, but we can assume, if we assume life is like this life, which is dangerous, but when we've nothing else to go on, it's as good as anything to work with, then we can make some educated guesses. But it's only some fraction of those planets will life actually evolve on. So we're getting a bit risky. We don't really understand these numbers now. And we have no idea, well, less idea the fraction of these where intelligent life develops. How many single-cell amoebas go on to have brains? And of course, if you're a really an advanced civilization, you might choose to not communicate with anyone. So you might not be seen. And then, of course, there's the end of the world one at the end, the fraction of a planet's lifetime that a society survives for. Who knows? May get a plague that wipes everyone out. Anyway, so you can just put all of these things together, and this is the Drake equation, or a version of the Drake equation, and you can multiply all these things together, and it can tell you, roughly, what kind of number of civilizations we're talking about. Now, the good thing about this, now I'm a scientist, so all of a sudden now this looks like an equation, which is something I can understand more. So some of these things, like the numbers of stars in the galaxy, the fraction of stars that have planets, FP, and NE, the number of planets per star that can sustain life. Well, we actually have, I'm going to say, good estimates. Now, this is astronomy. When I say good estimates, let me give you an example. The number of stars in our galaxy changed by a factor of 2 a couple of years ago. But that's okay. We're used to that now. This happens all the time in astronomy. These other numbers, FP and NE, so a fraction of stars that have planets around them, and the number of planets per star that can sustain life, well, we can now start making reasonably good estimates for them. These other ones, the fraction of these planets where life evolves, and the fraction of these where intelligent life evolves, we can guess, really. And the last two, those that choose to communicate, and the fraction of a planet's lifetime that society survives, well, we can just make educated guesses for. Anyway, so we'll come back to that at the end, because now we're going to have some real science. So we're going to talk about planets. Now, for years and years and years, people wondered about planets. People have been burnt at the stake for talking about this. But now we're allowed to talk about it and not get locked up, which is good. And that's because in the 1990s, in the last century, in the 1990s, the first planets were discovered. It was very controversial at the time, I've got to say that, but they were found. But it took many years for people to believe it. And the reason for that is this. The first planets that were found were like Jupiter-sized and Jupiter-massed, but in orbits of just a few days. And you compare it to our solar system, it's nothing like our solar system. And so we went out with preconceived conceptions about what we were looking for, and we found something quite different. So, of course, astronomers being skeptical, and there's a lot of inertia in the system, then, of course, it took many years, I think maybe 5 years before it was really accepted. And you're probably going to ask now, why don't you just go and take pictures of exoplanets? Well, this is a difficult thing to do. If you have a really bright light, like one of these, and you hold a candle next to it, you're not going to see it. So planets shine by reflecting light. They don't generate light of their own. And so they're always going to be a lot fainter than their star. And of course, they're a long way from us, and so they're going to be very close to their star and very faint. But after saying that, some planets have been imaged, extrasolar planets, away from our solar system. So these are a long way away, but they're very special. They're unusual planets. They're not like planets in our solar system. But it has been done, and in the future, it will become more likely. Now, there's been references to Doppler, so I thought I would bring this in. So this is a Doppler ball, right? Now, I haven't done a health and safety thing, but I'll just do it anyway, right? So, so anyone in the front rows, I apologise in advance if this goes wrong. So everyone has heard an ambulance, right? So this shows you this, well, this will let you hear the same kind of effect as it goes round. So you hear the pitch changing. As the ball comes towards you, it's higher pitched, and as it goes away, it's lower pitched. Well, so we can understand that in terms of diagrams like this. So this is sound waves coming off a source, and they come off in waves, in circles. But if you now give that source some motion, then you get this. And you can see the distance between the waves in the direction of motion gets closer together and further apart as they go away. Now, the same thing happens in light. It's really hard to measure, but the expansion of the universe was first measured by this, the red shift, right? That is a Doppler effect. But we can also measure it in stars. So you can see here's a star with another one going around it, okay? And you can see they're both orbiting the center of mass, right? They're not orbiting, one's not orbiting the other, they are both orbiting the center of mass in the... Oh. It's a good start. They are orbiting the center of mass in the system. And so at some points, the large star is coming towards us, and at other times, it's going away. And so at some points, the light is blue shifted, so it's higher pitched, if you like, and at other times, it's red shifted as it goes away. And from that, you can tell how massive the planet is, sort of. You can tell how massive it is relative to the star. So if you understand your star, you can make that measurement, maybe. Another thing we can do is actually measure the size of a planet relative to its star. And we do it through this. This really simple cartoon shows you a planet moving across our line of sight. Now, a star, of course, is not resolved. It's a point light source. But the planet will block out a bit of light. And the size of the dips, this is the star brightness here. When the planet goes across, it gets a bit fainter. Then when the planet leaves the disk, it gets brighter again. The size of that dip tells you how big the planet is relative to the star. So if you've got a bigger planet around the same star, then the dip is bigger. Or a smaller planet, then it's smaller. So, and it also tells you the most important thing is that we know that the orbit is in our line of sight. So the two things together, the measurement of the light changing, which is called the transit or eclipse, and the Doppler gives you the mass. So size and mass give you density. And that is the main thing you want if you want to compare with theoretical models. So here's a real astronomy slide now. And this is a diagram I want you to see. So here we have mass here and radius. And here's the Earth and Venus right down here. And here are some big planets that we've measured from the ground, actually. And here's Saturn and Jupiter. So these are compositions of different kinds of planets. So these are methane and hydrogen and helium planets over here. And so we have the tools now. If we can make those very simple measurements, in principle, we have the tools to be able to compare with theoretical models to understand the composition of planets that we're looking at. So from the ground, we can do these big planets, and there's lots of issues that have arisen. You can see that a Jupiter mass planet isn't necessarily a Jupiter size. Sometimes it can be twice the size of Jupiter, and we have no idea what's going on. So there's something, some sort of energy source in the planet, probably brought on because these are quite close-in planets. So diversity of planets seems to be a really big issue. We shouldn't assume planets are like the planets in our solar system. But to go to small planets, to go down here, it's very difficult to do from the ground. You need to go into space. So this is the Kepler spacecraft, which some of you may have heard of. And Kepler's done some amazing things. It's basically transformed this area. But just to show you what we're trying to do, this is the kind of measurement we can make from the ground. From space, we're trying to measure an Earth-sized object against the sun, and you can see the laser beam is bigger than the Earth. So this measurement from space is very difficult to make, and you need really particular good equipment to make it that you understand very well. You cannot do this observation from the ground, and from space it's tough as well. But Kepler was amazing because Kepler found loads and loads of thousands of different planets, or thousands of objects that had planetary size. But unfortunately, when Kepler was designed and built, people didn't understand that there would be such diversity. People thought, or scientists thought, that a 1 Jupiter mass planet would have a 1 Jupiter radius. And that's not the case. But there's still been some fantastic results. You can see this. Here's the size distribution. Lots of small planets, or lots of probably small planets from Kepler. But also lots of planets in multiple planet systems. Really amazing, because it means that these planets are in systems that are incredibly flat, so that you get multiple transits from different planets. That wouldn't happen in our solar system if you could see it. So these are amazing results. And here's a multiple planet system. This is something called Kepler 11. Here are the transits. So going back to that original diagram, we're now looking at this again. So here's mass and radius, and our Jupiters are over here somewhere. And here's Earth and Venus, and this is where we are, down here. These are the best measurements available at the moment. So I think one of the shocking things is that the diversity of planets, of small planets, continues. But maybe that isn't so surprising. Just imagine you take a planet like Jupiter, which has a solid core, and you bring it in next to its star, and you fry it in a 4-day period, and all the stuff comes off it, and we see planets that are evaporating, and you're left with a core. And that core will be super dense. And that's what we find in some cases. So there's great diversity of planets over here. How common Earth is, we still don't know. So I thought I'd put this in about alien megastructures, and I know the guy that was responsible for this, and he's deeply embarrassed. And the reason for that was because they had found this object. This is the Kepler light curve of it. It's actually, the variations are big enough, you could see these from the ground with an ordinary telescope, no problem. So this is over a few years, over 1,500 days. He made some sort of jokey comment to a journalist about how this is probably some aliens. And so a whole new industry was born. Who wants an alien megastructure today, whatever that is? And this is the sort of stuff, if you go and do a search on Google on alien megastructures, there's many, many more references to that kind of stuff than any paper I've ever written. It's completely demoralizing as an astronomer. But the reality is we're probably talking about a natural phenomena, although we don't really know what it is. It's probably maybe some groups of comets or something like that. And there are other things in the Kepler database and in other databases that actually look quite similar, but they've never been called alien megastructures. Anyway, so let's move on. Habitable zone planets. Now, this is when it's starting to get sexy stuff. If I go to the journalist and say, I've got this habitable zone planet, then before you know it, it's in the newspapers. And Earth 2, for the 20th time, is born. And this is why. It's really quite a simple concept. It's astronomical habitability we're talking about now. And all that means is at a distance from the star whereby the temperature at the surface of the planet would be able to sustain liquid water. Now, Venus, that well-known habitable planet, is also in the habitable zone, despite its 600 degrees C surface temperature. So this is one term for habitability. As we get better at this game, we'll have better definitions. Clearly, we need to talk about atmospheres and things like that. But anyway, after, I guess, about 20 years now, this is what the habitable zone gallery looks like. And what I would say is that for many of these objects, the sizes are well-defined. Anything that says Kepler has a well-defined size, but a lousily defined mass. And it could be a little gas ball, or it could be a little Earth-like planet. And anything that's not called Kepler, so like this one over here, for instance, has a reasonably well-defined mass, but we've no idea of the size. So Earth 2 is still out there, and sooner or later we will get to it. Now, I just wanted to say something about some of the bigger discoveries. We've heard even reference, I think it's in Chris's talk, to Proxima b. So this is the data that gave rise to the discovery of Proxima b. Now, the important thing about Proxima b is that it's the nearest star. The nearest star has probably a planet. This is the data. You can see the orbit that's fitted through the data. But again, we've no idea the size of the planet because it doesn't transit. But it's probably, I mean, there's probably something there. But again, someone spoke to a journalist and you saw what happened. But the great thing about this is that I'm sure this is true. Let me say that. I'm sure this is true because planets are just the muck that's left over after stars have been formed. So we are composed of pre-solar muck. We're the stuff that's left over after a planet's been formed. So after a star's been formed. And then the other one that's got a lot of mention recently is TRAPPIST-1. Now this is amazing because there are, I think, 7 planets in this system. 3 of them are at habitable zone distances. But again, this is a very special case because this star is unbelievably low brightness. It's nothing like the sun. It's a tiny little star, only just sustainable as a star. And so, because it's a small star, you can see small planets around it. It's also very difficult to do any other observations with it, but it's very, very interesting. And there's going to be a lot of fun to be had with this system and similar systems over the next few years. Oops, forget about those. I want to show you this. So, how can we find out about atmospheres of planets? Well, there are simple ways to do it, all very difficult, let me say that, because we're trying to look at very small effects. But one way that's reasonably well established now is this idea of reflection. So if you imagine, just like the moon changes phases as it goes around the Earth, well, a planet, as it goes around the star, like this, will also change its phase as we look at it. So when it moves across the face of its star, well, it's a new planet at that time. It's a black dot crossing the surface of the star, and you get a transit like that. But then it goes round, and at the other side of its orbit, the star goes in front of the planet. But you can see that because there's a little bit of reflected light, a really tiny little bit of light, that as this planet goes round, you expect the total light from the whole system to change very slightly. And if you look up here, you'll see there's a little sinusoidal curve going on over here. So much so that when the star goes in front of the planet, at this stage over here, then you get another little dip from light from the planet that has been blocked. So this light above the transit is actually coming from the planet, and that's really important. So normally we're just blocking out starlight, but in this case, it's light from the planet. And so you would expect a sinusoidal variation as the planet goes around the star in the light. Very small, very difficult to see. So I'll just show you these results. These are published in Nature this year. And these are orbits, separate orbits of one particular big planet. And as it goes round, you see a transit, and you see another little eclipse when the star moves in front of the planet. And it goes on and on and on. And you can see they're changing. Now just imagine if you have a ball of gas which looks the same all over, then the sinusoid will be the same all the time. Now just imagine if part of it had dark material on, then your sinusoid will change. And changing atmospheres is called weather. So this shows that these are right at the limit of what's possible, let me tell you, with Kepler. It shows that the sinusoid changes over the lifetime of the Kepler mission. So we're seeing weather actually occurring on this planet. Anyway, exoplanet science is actually becoming of age. The time of discovery is, well, it's still going on, but we're interested in characterization now as well. But I just want to show you some of the missions that are coming up, because you're going to be hearing about these over the next few years. And I think the big one that's coming is James Webb Telescope. And this will be useful really for trying to study the atmospheres of some of the nearest planets. And there's going to be some really interesting results coming out of that. And finally, I'll just say something about ESA, the M3 Plato Mission, which is about 2025 or so. And that is like a super duper Kepler on steroids, designed to find planets around nearby stars. And no doubt you'll hear a lot about that. It's quite different to Kepler, but Earth too will come, at least from this mission. Just to quickly say, it works by, it detects transits around planets, but it also attempts to characterize the star. Because if you remember, I said all these measurements were relative to the star. So you need to understand the stars incredibly well to understand your planets. And it does this using seismology to understand the stars. Just like if you make an explosion on the Earth, the wave propagates through the Earth, and you can understand the internal structure of the Earth. Well, stars also vibrate, and those waves, as they propagate through the star in these really contorted fashions, allow you to understand the internal structure of stars. Yeah. And if you can understand the internal structure of a star, you can understand how much hydrogen is left in the star. And if you can do that, you can determine how old the star is. So for the first time, we'll be able to understand the ages of our planets as well. And so we can start to try to understand the population of planets going forwards. Then, how do you find life? Well, this is not a trivial question. The idea is you look for biomarkers, markers that indicate life is there. There is some disagreement on what biomarkers are. I think now we have missions that are capable of either searching for these planets or able to record the light from these planets. Then there will be a lot more work over the next few years to understand what biomarkers really are. But suffice to say, and I always feel very sad when I say this, the easiest planets to find life on are the planets where there is the most pollution. And that's because things like vanadium, blah, 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 only comes from artificial sources. So if we find something with exotic species in, it's probably artificial in some way. This is an amazing picture, this is from one of the pioneers looking back towards the Earth. It's called the pale blue dot picture from Carl Sagan. Shows the Earth from a long, long way away. Anyway, so let's go back to our original question. And let's try and put in some of the numbers that we know about. Okay, so number of stars in the galaxy, is it 200 or 300? 200 is good enough. Fraction of stars that have planets around them? Well, I think this is 100%. But anyway, let's be conservative and put 50% in. Stars all have planets, I'm sure. Number of planets that can sustain life. Now, we have some idea of this. Kepler gave us an idea. From Kepler, we know it's either 2% or 120%. But hey, it's astronomy, that's pretty good. But if we want to understand it, then we need to look a bit closer. But anyway, so we'll assume there are 3 or 5 planets in the habitable zone, something like that. Fraction of planets, okay, so now we're getting into the realms of fancy a bit. Let's say 50%, we're guessing. 50% where, I mean, these numbers could be a lot smaller or a lot bigger. And this one, well, fraction of a planet's lifetime that society survives in. Yeah. Okay, well, anyway, so we'll put those numbers together and we come out with a large number, a relatively large number. Remember, that's in our galaxy, and that doesn't mean there are 20,000 civilizations existing now. There have been 20,000. It's probably quite likely that we're the only civilization like ours around at the moment. So that's a bit depressing. But these numbers could easily be wrong. It could be many, just they're being very quiet. Anyway, the good thing is we have the capability to find these planets, and we have the capability to characterize these planets. And over the next decade, you're going to hear a lot about this. We have to keep the press under control, so they only report on the most important things, but the science has reached a maturity where we can do this. We can start looking for life. My prediction is that unless we find something in the solar system where we can go in situ and find life, then if we're looking for extrasolar life, 2030, that's what I reckon. And the last 2 things, well, what I would say is that people have dreamt about what we're trying to do now, since people could dream. So we live at a very special time. And I think these sort of questions, which again, you probably have been burnt at the stake for asking a few centuries ago, these are now legitimate questions to ask. And in our children's lifetimes, I think we'll start being able to answer these questions. So, and that's it. Too long?
We have 1 or 2 questions to keep ourselves reasonably on schedule. There's a couple here. Let's try those 2.
I'd like to know more about the 120% of planets, please.
Yeah, I'd like to know about them as well. No, I mean, seriously. It's probably quite likely that different kinds of stars have different numbers of planets. And the reason for that is that if you imagine a small star, it comes from a relatively small disk, right? And so it's very unlikely you would make really big planets in that disk, although we have exceptions, right? But you'll probably make lots of small planets. But for every big planet in our solar system, you can see there are lots of small planets. So the 120% could be, well, that's above a certain size. That's the detection limit. Those are Earth-sized objects. And it's because when you look at the numbers, they're the most difficult objects to detect. So you have to fold in lots of corrections into your data. And the object, this was right at the limit for what Kepler was capable of doing. And so if I do it, I get 2%. If someone else does it, they get 10%, et cetera, et cetera, et cetera. I mean, you know, we know of one case where it's real here. There are several planets in the habitable zone here. I think there'll be many. So,
And one more just here.
In your first or second slide, there was this line, which is a strong statement. If there are other civilizations out there that are likely to be millions and millions of years more advanced than us, but what is the actual statistical?
No. What I said was, if there are other civilizations we can communicate with, they will be millions of years more advanced than us. Because the likelihood is, from the statistics, that we've only been able to communicate for 150 years, right? To find another civilization at our stage is really unlikely. They're going to be either not able to communicate with us, or blown themselves apart.
Thank you, that answered.
Is that okay?
Again, maybe catch Don at the break if you have any further questions. I know it's a very exciting topic, and a lot of astronomers are really, really excited by the sort of things that Don and his colleagues are doing. So thanks again, Don.